Good morning, good afternoon, good evening, wherever you are in the world, and welcome to this DSP online conference talk on fractional delay Farrow filters. My name is John Edwards. For those that don't know me, and I'm sure some of you have seen this slide before, I'm not the former US Senator and Vice Presidential candidate who got caught doing something he probably shouldn't have done. The world of DSP is not quite so interesting. I have been involved in digital signal processing since the very early 1980s, involved in comms and noise, radar, sonar, all sorts of different application areas. And I now work as a consultant in that space. I am the author of the SIGLib DSP and Machine Learning Library. And basically that is all of the code I've written, the non-proprietary code, over the last 40 odd years. And it's free to use for personal and educational purposes. As well as that, I'm the course director at the University of Oxford for the annual Digital Signal Processing course, which has been running since the early 90s. And I present courses to companies and present papers at conferences and so on. So, welcome to this talk on fractional delays. We're going to have an introduction to fractional delays. We're going to talk about some interpolation methods that we could use. Then we're going to focus on the Farrow structure, and I'll explain its benefits and disadvantages in some application areas, and we'll talk through the whole development process of a fractional delay Farrow structure, and we'll end up with a demonstration. Okay, so fractional delays. Depending on our application, we might need to add or delete single samples between existing samples or multiple samples between our original input samples. And how we go about doing that and the algorithms we use is very dependent on the actual application requirement. For example, in some applications, we might, such as asynchronous sample rate matching or delay matching, we may just be required to add or delete individual samples. But in other applications, such as sample rate conversion, we might need to add or delete multiple samples. And the actual algorithms we use will depend on the particular application. Some of you, and hopefully all of you, will have seen Dan Bichen's presentation in which he expands basically on this slide to talk about the differences in many of the different algorithms. And it's almost like Dan and I got together a few months ago and discussed these topics, and his beautiful introduction, which leads nicely for the first scenario, sample rate matching, delay matching, etc., to my talk on the fractional delay Farrow filters. It wasn't planned, it's just beautiful synchronicity that's just happened this year. So if you haven't seen it, please go and see Dan's talk. He gave me a quick overview, and it's, as always, excellent. So we are going to talk about the scenario of adding or deleting a small number of samples, typically just one sample between existing samples for applications such as sample rate matching and delay matching, etc. Okay, fractional delay filtering. As the name suggests, this is an algorithm or a technique that delays a discrete signal by a non-integer number of samples. In reality, this can be very easily implemented for a fixed delay using simple FIR filters. And some examples of the interpolation algorithms that you might use are listed here. Lagrange interpolation is a very popular algorithm that uses polynomial interpolation to approximate the delay between the samples, to interpolate between the samples. Very simple to implement, can be implemented using an FIR filter, as can some of these other algorithms such as FIR least squared or a window sync filter design. We can, all of these algorithms listed so far use finite impulse response filters, but we can also use infinite impulse response filters. Now, these are all very well if you have a fixed delay that you need to implement for your application. But the question arises, what happens if the delay needs to change during your application execution? And that's where the Farrow structure comes in. So, before we go on to look at the Farrow structure, I'm going to present a few different interpolation methods that are very common that we might like to use. The first one I'm going to talk about is Lagrange interpolation, which is just polynomial interpolation between a set of points. The Lagrange polynomial is just a unique polynomial of lowest degree, i.e. it's sort of the minimum number of coefficients really to get a good interpolation. We can use Lagrange polynomials of different orders depending on the specific requirements, and of course the number of coefficients in our filter n is going to be equal to the order of the polynomial plus 1. For the best results, the delay that we are going to accommodate, the maximum delay, we're going to accommodate in our Lagrange interpolation filter should be approximately plus or minus 1 sample period from half the length of the filter. So depending on the delay you need to implement, you may require a longer or a shorter delay. Just to give you the sort of basics of Lagrange interpolation, if we have a first order Lagrange interpolator, i.e. 2 coefficients, that's effectively linear interpolation, i.e. given a position between our 2 points x0 and x1, then we are going to linearly interpolate the points between those two. If our desired point is exactly halfway between the two, then of course the result is the average of the two numbers. So it's very easy to implement, but a first order linear interpolator is very basic. It doesn't give you good transition at the edge points. So you might want to consider more higher order interpolators, such as quadratic or cubic interpolation. In terms of interpolation and requirements, the ideal interpolator will have a flat frequency response, i.e. be an all-pass filter. All frequencies will be interpolated equally, and of course it will also have a linear phase response, so that all of the frequencies exhibit equal delay. These requirements tend to suggest, or certainly the last requirement tends to suggest, an FIR filter is the best fit. Of course, anytime we filter our data, we're going to have to restrict the length of the filter to some number of coefficients that are implementable on our DSP. And so our ideal scenario of having a flat frequency response is something that is often very difficult to achieve in reality. There will always be some kind of trade-off, particularly at the high frequency end of the scale. So as we go through the talk, think about these issues, and then we'll see them demonstrated in the demonstration at the end of the talk. Okay, so how do we compute the Lagrange polynomial coefficients? Well, here is a simple example for second order, i.e. the number of coefficients equals 3, and actually you can see how the interpolation of the values is computed using these three elements. So for example, if we have a given set of known input points, x1, x2 and x3, and a given output points y1, y2 and y3, then using these equations for a given input value of x, we can compute the polynomial to compute the interpolated point at this position px. So x1, x2 and x3 are the known points of our data set. y1, y2 and y3 are the known locations on the y-axis. And x is the delay position we would like to interpolate our values. Excuse me. So essentially the Lagrange filter is a set of coefficients that allows us to compute the output y for a specific delay of x. So if we desire to support multiple delays, we would, using this algorithm in its basic form, we would require separate filters for each delay. Should you wish to compute the coefficients, here is a very simple piece of Python code that allows you to compute those coefficients for any filter length and any delay. And as I kind of hinted earlier, there's obviously a balance between achieving a good fit and maintaining a smooth, well-behaved function and increasing the degree of the polynomial, i.e. the filter length and the number of MIPS that it's going to take. So there's always a trade-off in all of our DSP applications. Okay, so another interpolation algorithm that we could consider for these types of applications is the cubic Hermite spline interpolation, which constructs smooth curves between the data points by specifying both the function values and the derivatives at each point. And that's an important thing, as we'll see in the next slide. Essentially, for the cubic Hermite spline interpolator, we have our given set of points, just as we did with Lagrange, but we optionally can specify their derivatives at those points. So the cubic Hermite spline constructs a cubic polynomial for each individual, i.e. between two data points on our data set for a given time t, where t is between the value 0 and 1. And then we have this polynomial using the showing the basis functions. The basis functions are shown here. And we're basically incorporating both our input samples and our output samples y on the y-axis, known points on the y-axis I should say, and our slope, our derivatives. And using that, we can generate our point on the for the output. The basis functions are shown here. They're just simple equations based on that time value between 0 and 1. Again, just like the Lagrange interpolator, for each delay we need to compute, we will need to compute a polynomial, a filter, a set of filter coefficients to calculate that delay that we require. But as I say, the benefit of the cubic Hermite spline interpolation is that we can specify the slope or the tangent of each point going into the interpolator. So that adds an extra level of functionality that we can use. Okay, so that's two of the most common interpolation algorithms. What we're going to do now is we're going to look at the Farrow structure, and in particular we're going to see how that gives us, if you like, extra functionality whereby we do not have to compute these separate filter coefficient sets for each of the delays that we need to handle in our application. So the Farrow filter structure is high level, is a very computationally efficient method for delaying a signal by a non-integer number of samples, but it allows for the adjustment of the fractional delay without redesigning the filter. So with one structure that we design, we can support any fractional delay within our range of our design. So it's a very efficient solution when we need to vary the delay. For these types of applications where we do need to vary the delay, it's generally a much more efficient solution than using multiple FAR or IIR filters to handle lots of different delay possibilities. It's very flexible, as you'll see, but it is not necessarily the most efficient algorithm for applications such as sample rate conversion, etc., where you might have much higher performance using algorithms such as polyphase filters, multi-stage designs, CIC filters, etc., etc. And of course, Dan's talk is going to be covering much of those points. And for those applications, polyphase filters and applications such as that, of course, Fred Harris is the expert. But back to the Farrow filter and the Farrow structure. Applications where this is ideally suited are beamforming, digital communications, timing synchronization, for example, audio effects, sample rate conversion, particularly if we are connecting two clock domains, as I mentioned before, with separate asynchronous clock sources. So how does the Farrow structure work? The Farrow structure approximates a set of impulse responses, polynomials, based on a single parameter mu. And mu is going to be the parameter that controls that variable delay, that fractional variable delay. Essentially, as you'll see when we see the flow diagram in a second, it uses a bank of FIR filters to implement a number of fixed delays where the coefficients of the filters are simply Peath order polynomials that could be designed using either of the interpolation algorithms we talked about earlier. But with the Farrow structure, what we do is we filter all of the data samples through all of the filters in parallel, and then we combine the outputs to compute the fractionally delayed sample. Now, you might think that's going to add a lot of complexity because we talked about these interpolators and how you need a separate filter for each desired fractional delay. But if you take the approach of using separate filters, you need a lot of filters, and they're generally quite large, so they'd be larger order. However, one of the benefits of the Farrow structure is that actually you can implement these fractional delays using very low order filters, and it's combining the outputs of these lower order filters that gives us a really accurate result. So let us go and look at the flow diagram for the Farrow structure. And that is shown on this slide here. And here we see we have, let me just turn on my pen. We have our 4 filters in this case. So this is a 4th order Farrow structure, 4 filters. And then at the bottom we have our combiner. And the combiner works by taking this control parameter for the delay, mu, and multiplying or scaling each of the outputs of the filters, and then combining, just with a simple addition operation, each of those outputs. So each of these filters that you see here has a different delay characteristic. And so we filter our input sequence through all of these filters. So the outputs of each of these filters effectively has a different delay. Then when we combine those delayed outputs, what we end up with is our output, which is delayed by the amount defined by our control parameter, mu. That sounds good, and indeed it is, because that's what we're going to talk about. We'll demonstrate it. But at the moment you might think, well, there's a lot of sort of unknowns. How large are these filters? What order system do we need? And we'll come on to answer those questions. So looking at those, that flow diagram in a more equation-oriented approach, each of those subfilters is a completely standard FIR convolution filter. We have our input sequence, x of n, which is then convolved with our coefficients, g of n, to give us our output. So y k of n, so where k is the number of each subfilter, 0, 1, 2, 3, in this case of the previous example, previous flow diagram. The variable delay is then implemented by combining the outputs of the filters, shown here, where mu is the fractional delay, hk of mu are the polynomial coefficients depending on the fractional delay, and k is the interpolation order. Now, the interesting thing is, if we go back to the previous diagram, what we see is that as we take our input mu, let me just clean this diagram up a second for you, and we take our input mu, which is used to multiply all of the all of the partial results, sorry. So this, if we take the output of the first filter coming out of here, we multiply that by mu. We then add it into the output of the second filter, and then that combined result is then scaled by the control parameter mu. So effectively, the data coming out of the first filter is now scaled twice. And so you can see that as we pass down the filter, the outputs from those earlier filters, the scaling will vary dependent on that mu parameter. And so if we just think about taking 2 points and having a linear interpolator, so a first order, then the scaling between those points, this would be x0 and x1, will depend on the mu factor, and the amount of impact each one has will depend on that control mu factor. Okay, so let's think a little bit more widely before we go on to look at the filter coefficients in more detail about applying this filter. Well, the first thing that you might need to think about in many applications is the scale of your delay. How large is your delay going to be? Is it always going to be a fraction between 0 and 1? Or might your delay be larger? Again, a variable delay. For example, maybe your delay lies between 2.3 and 5.6. In this case, we need to support integer delays. Now, we could design a Farrow structure that supports these large ranges of delays, but often it's more efficient to separate the integer and the fractional component of the delays into two separate components. So the integer component of the delay we'll just implement using a simple FIFO buffer, and then we'll support the fractional component using the fractional Farrow structure, as we'll talk about in a bit. If we take this approach, and of course, as ever with DSP, every different approach has its advantages and disadvantages, but if we take this approach of separating the fractional and the integer component, the one thing we need to remember is that every time we cross an integer boundary of our input sample dataset, then we need to either push additional samples into the state arrays of the fractional Farrow structure, or pop, i.e. derotate, unwanted samples out of the state array. And in fact, if you need to do that, very often I've found one easy way to do it is to keep a separate state array, which is which keeps a history of the input samples, which is greater than the largest delay you will need to support in your application. And so you will always have enough samples to either push additional samples in or pop, derotate samples out of the those FIR filter state arrays. Okay, so in order to be able to use the output from the fractional Farrow filter, particularly if you have multiple channels with different delays or some other scenario like that, then the filters must be causal, i.e. the minimum delay through the filter structure must be greater than 0. You'll see how that impacts our output in a few minutes when I show you the demo. And of course, that extra delay, whatever those extra delays are through the filters, must be compensated for in any synchronized channel scenario. So that's sort of the sort of background details and the high-level details of the fractional Farrow structure. What we're going to do now is we're going to look at how we use these interpolation algorithms to design the coefficients for our Farrow structure. So first thing we need to do, kind of touching on the slide that I have just talked about, we need to identify the delay range and the precision required. From that we can determine the polynomial degree and the filter length. We need to choose our polynomial basis, Lagrange, Hermite, many different possible solutions. In this talk I've just talked through the two main ones that we're most likely to use for these types of filters, that's Lagrange and Hermite. And then we need to design the filters for each set of polynomial coefficients. And we can use many different design techniques to design those coefficients. Actually, the reality is, as I found, there are coefficient sets available that you can choose. Finally, we might need to normalize our coefficient sets to ensure our desired gain and stability. So some of the coefficient sets that I first tried when I was researching into this a few years ago was that some of the filter coefficient sets that I found on the internet and so on ended up with different delays of data and giving different gains to those data sets. So the gain through the filter would vary depending on the delay. And one of my early implementations, I ended up having a sort of delay compensation little piece of code, just a couple of lines of code at the end, to normalize the delay, the gain through the filter dependent on that delay value. So we need to choose our delays, our coefficients wisely. As I say, you can choose coefficient sets that can support large delays, but actually I've found it more efficient to separate out the integer and the fractional part of the delay element. Okay, so Lagrange. This is a table you'll find in many of the documents where typically I've seen for Lagrange, these documents will use D for the desired delay as opposed to mu, which I've been using so far in this slide. And this, for a given delay, if you, depending on the order of your Farrow structure, then you this gives you the coefficients for your the values for your coefficients, H0, H1, H2, etc. And I've given an example here how, for example, with a third order filter, you might choose the values the delay, the nominal delay values of 1, 1.33, 1.666, and 2 as your delay values to compute the interpolator values using the values shown here. And there's some references to show you that. But I did try that in the application I was involved with, and also I tried a set of values that are described by well-known person in DSP field, Robert Bristow Johnson. Here's the reference to one of his many discussions on this subject. And what I ended up using was the cubic Hermite spline interpolation, which, as we saw in the previous discussion, is C1 continuous, i.e. the slope is continuous across our nominal sample points, contiguous across our nominal sample points. Another benefit I found with this is that the output levels for all signals are all unity gain, and RBJ's coefficients are shown in the slide here. So as per my other talk at this conference this year, I subtitled that Standing on the Shoulder of Giants, and I should apply that subtitle to this talk today as well, because I take no credit for these numbers. I found them, used them, and they did exactly what I was looking for. So with that, let us go and have a look at a demonstration. And by the way, so this is Python code, as you will see. This code with the slides and everything will be available to download off the conference website, so you can go and download it. You can play with it, modify the values and play with it to your heart's content. Okay, so here I've got the code we showed before for the Lagrange coefficients. Here's my code for applying the Farrow filter. As you can see, it's a very easy piece of code. We're just performing a convolution filter function, and then we have our delay value multiplying in the samples, and then this is really our test function, sample rate. What I'm just testing with a simple sinusoid. You can choose whatever kind of signal that you like for testing this once you've downloaded the code. Here are the RBJ's coefficients. I just print them out because you can try different sets of coefficients, and then here we apply the fractional Farrow filter here, and we plot the results, and here are the results. So what do we see? Well, over on the left, the first thing we see is that there is always a unit sample delay. Of course, there, this filter is has a delay, group delay through it, and so even if we choose the input delay as 0, there will be a group delay through those filters, and then subsequent to that, we have the actual delays for each of the values that I've chosen here. So I've taken the original signal, I've ran it through the Farrow structure 10 times, and you can see the delays all nicely spaced out there. Now, that all looks great, doesn't it, with a simple 1 kilohertz input signal. But when it comes to testing, there is a lot more to testing a fractional Farrow filter. As with any filter, there's more than just running a sine wave through it. We need to look at the phase response and the group delay. And here we have our phase response graph. And of course, you can see these are all nice and linear. with obviously the phase delay being dependent on that mu factor through the filter. But interestingly, as we get up to the higher frequencies as we're approaching Nyquist, you can see that these tend to diverge. And actually that is much more obviously displayed in this graph here, where we are showing the group delay of those different interpolated samples. So here you can see really below about half Nyquist, the group delay is excellent. It's very close to what we would expect. But then as we go further towards Nyquist, we see that the group delay of the different filters are diverging. So what does this mean? What it basically means is if you want full bandwidth, fractional variable group delay, you might need to implement a higher order filter. You can easily do that. You've got the equations in the slides. You can go and find them on the internet, I'm sure. But actually, if your frequencies of interest are certainly well below half Nyquist, then even this very simple third order fractional Farrow filter structure gives you a very, very good approximation to that fractional delay requirements that you need. Okay, there's the delay. There's the demo. Feel free to download it, have a play, ask questions on the on the chat on the conference website, and I'll certainly do my best to answer any questions you have. So on to a quick summary. The beautiful thing about the fractional delay Farrow filter is you just have a single parameter that allows you to adjust the fractional delay. You don't need to run, apart from the filters that we've shown, you don't need to run many multiple filters to support all of the different delays you require in your application. RBJ's coefficients are a very strong baseline for low to mid band delay with high accuracy, but you may require higher order interpolators depending on your requirements. So when designing a fractional delay Farrow filter, the kind of performance metrics that you should look at measuring: noise floor with a sine wave, with a more complex waveform, the resolution of the output, the phase, particularly if you're using fixed point device, of course, the phase response, the group delay, and so on. And if Python is not your thing, feel free to go download the code off my library and have a play with that. So here is a short list of some of the giants whose shoulders I've stood on top of. Of course, Farrow. Without him and his work, we wouldn't have a Farrow structure. But no talk at the DSP online conference would be complete without a reference to a paper of Fred's. So here's one that I read quite a while ago. Laxo, very good general introduction to fractional delay filtering in the IEEE magazine. RBJ's paper and Julian Smith's website as well. Okay, with that, thank you very much for your time. Enjoy the rest of the conference, and goodbye.